exploring the mysteries of Enceladus, unraveling the secrets behind its plume. Enceladus, Saturn's icy moon, emits a unique plume from the South Polar Fault System, nicknamed Tiger Stripes, which is linked to a subsurface ocean. Our study reveals how periodic modulations of plume activity shed light on the dynamics of these water-filled faults. A medium-sized moon of Saturn with a diameter of about 500 kilometers has long captured the attention of researchers due to its fascinating characteristics. Located near Saturn's main rings, Enceladus became a subject of intense study after the Cassini spacecraft discovered jets of water vapor and icy particles being ejected from its south pole. These plumes are emitted from 4 main faults at the Moon's south pole, giving scientists a rare opportunity to sample material from the subsurface ocean beneath Enceladus' icy crust. This discovery raised profound questions about the Moon's geological activity and the potential for life in its hidden ocean. Despite significant research, the dynamic processes driving the variation in the eruption activity of these plumes have remained unclear. However, new insights have emerged thanks to advanced numerical models that simulate Enceladus tidal deformation and detailed analyses of processes within its fault zones. By combining these global and local perspectives, researchers are now beginning to understand how the plume activity changes over one complete orbit, and what this variability reveals about the ejection of oceanic materials into space. The enigma of plume variability. Since the discovery of the plume on Enceladus, scientists have noticed that the intensity and timing of the plume's brightness change along the Moon's orbit. It seems that the activity of the plume is influenced by tidal forces exerted by Saturn. Enceladus orbits Saturn once every 32.9 hours, during which time the gravitational interaction between the Moon and the planet causes Enceladus' ice shell to flex. This flexing results in the movement of the walls of the Moon's faults, creating stress in the region around the South Pole. Yet, while it is clear that tidal forces play a role in the plume's activity, the exact relationship between these forces and the observed variations in plume brightness has been elusive. Earlier studies suggested that the changes in plume brightness, which reflect the amount of material being ejected from the Moon, are directly related to the varying stresses within Enceladus' ice shell. However, the observed pattern, which features 2 distinct peaks in activity during each orbit, did not match any of the proposed models. This discrepancy suggested that more complex processes were responsible for the variability in plume emissions. A new approach to understanding Enceladus. In response to this puzzle, researchers recently adopted a novel approach by combining global and local modeling techniques. On a global scale, they developed a 3-dimensional numerical model that simulates how Enceladus' ice shell deforms in response to Saturn's tides. This model captures the large-scale tidal stresses that affect the entire Moon. On a local scale, a 1-dimensional model focuses on the specific processes occurring within the fault zones where the plumes originate. This local model quantifies how liquid water, vapor, and solid ice particles move through the fault zones, factoring in both the direct jet-like flow of material and a more diffuse flow that seeps through smaller cracks and porous materials. By connecting the global deformation model with this detailed local model, researchers have gained a better understanding of how material is transported through the ice shell and eventually ejected into space. Key findings and their implications. One of the key discoveries from this research is the identification of 2 distinct mechanisms that govern the behavior of Enceladus plumes. The first mechanism involves the horizontal displacement, or slip, along the Moon's faults. As the ice blocks on either side of a fault move relative to one another, they create pathways through which water vapor and ice grains can escape to the surface. This process is particularly effective at producing the jet-like emissions observed in the plume. The second mechanism is controlled by the normal stress acting on the faults. This stress affects how material moves through more diffuse channels in the ice, leading to a more gradual, ambient release of plume material. Together, these two mechanisms provide a more comprehensive explanation for the plume's behavior. The model developed by the researchers successfully replicates the observed pattern of plume activity, including the two distinct peaks in activity during each orbit and the timing and relative intensity of these peaks. This breakthrough represents a significant step forward in understanding the complex dynamics that drive plume activity on Enceladus. By combining global tidal forces with local fault processes, scientists now have a clearer picture of how the moon's faults influence the plume emissions observed from space. Looking ahead, the future of Enceladus research. The findings from this study not only enhance our understanding of Enceladus' current behavior, but also have important implications for future exploration of the icy moon. Understanding the precise mechanisms that control plume activity will be crucial for planning future missions. For instance, knowing when plume emissions are most likely to occur can help mission planners optimize the timing of flybys or lander missions to maximize the chances of sampling fresh material from Enceladus' subsurface ocean. In addition, continued observations of Enceladus are essential for refining our models and deepening our understanding of the moon's enigmatic nature. The James Webb Space Telescope, JWST, is expected to play a crucial role in this effort. With its advanced instruments, the JWST can provide high-resolution data on Enceladus plume activity from afar, allowing scientists to test their models and further unravel the mysteries of the moon's subsurface environment. Conclusion: Enceladus has become one of the most exciting objects of study in our solar system, thanks to its active plumes and the potential for habitability within its subsurface ocean. The research conducted so far has provided remarkable insights into the processes that drive the plume activity on this small moon. By developing a comprehensive model that integrates global tidal forces with local fault dynamics, scientists have made significant progress in explaining the variability of Enceladus plumes. However, many questions remain unanswered, and future missions and observations will be critical to advancing our knowledge. The more we learn about Enceladus, the closer we come to understanding whether this intriguing moon could harbor life, making it a prime target for future exploration in the quest to discover habitable environments beyond Earth.